now we will discuss one of the probabilistic models, and this model is based on the idea that the network actually follows, a network is constructed based on some sort of hierarchical structure. Okay. A network is said to be a network is said to be a hierarchical network if nodes can be divided into groups. Each of these groups can further be divided into subgroups and so on. Each group formed in a logical order corresponding to a granular functions or social unit, right? And this is well accepted, at least from the last chapter on community analysis. You must have understood that network actually contains some inherent hierarchical structure. We have bigger community, then smaller, then further smaller, and so on and so forth. And the notion of hierarchical community and the formation of a network, these are interrelated. So here the idea is that can we given a network, can we unfold the underlying hierarchical structure based on which a network is formed? Okay. So basically we will try to come up with such an hierarchy, right, which would tell us how this network was formed. Okay. In that aspect, this is also a generative model, because based on the hierarchy, let us assume that we know the hierarchy. Based on the hierarchy, we will generate the network, and we will see that the network generated by the hierarchy at all matches with the network that is already given to us. Okay. But there are many questions that you can understand, that how do you generate the hierarchy, from hierarchy how do you generate the network, and so on and so forth. Okay. So in general, when we look at this hierarchy, we call this hierarchy as dendrogram, and dendrogram is a very famous, well-known term which generally is used in the context of clustering, right? You may have heard about this hierarchical clustering, where is called single link partition, all these link partitioning methods and so on. All right. So again, what is the target? The target is that given a graph G, the target is to come up with a decent dendrogram, decent hierarchy that explains the network generation process. Okay. And the hope is that when we get the exact dendrogram, right, we should be able to know that what is the probability that two nodes will be connected, because this dendrogram itself is responsible for creating a graph, right? Now then of course you will be able to say that given a particular pair of nodes, what's the probability that they will be connected in the future. Okay. So what do you mean by a dendrogram here? Let's assume that this is the graph. Okay. Now from the graph, you can actually create infinite number of dendrograms, exponential, not infinite, at least exponential number of dendrograms. Okay. And each of these dendrograms would look like this. So this is one dendrogram, dendrogram D1, hierarchy D1, right, where leaf nodes are the original nodes present in the graph, right. So there are 6 nodes, right, and according to this dendrogram, A and B are connected first, then C is connected, then D is connected, right, with the process, right. I mean, what I'm trying to say is that first A and B are connected, then C also got connected with A and B, then D got connected with C, and so on and so forth, right. And each of these internal nodes, it sounds little bit tricky to understand, but you just follow what I'm saying. At the end of the lecture, you will understand what does it mean. Okay. So each of these internal nodes, right, indicates the probability, the association probability, how likely two nodes or two groups, right. When I say that, what about this node, because this node connects a group to a node, right. What is the association probability, what is the likelihood that two nodes or two groups are to form a connection, okay, in the original graph. Given that R, so say let's say this is R, okay, R as their least common ancestor, okay, because if you look at it carefully, A and B and C, they may also have this as a common node, common ancestor node. They also have this as a common ancestor node, right? But which one is the least one? This is the least one. This is the recent one. If you move from bottom to top, this is the recent one. Okay. Now you may ask that how do you come up with this hierarchy, right? I can connect these nodes in a different manner. Yes, that can also be possible. Let's look at this dendrogram. Here, if you see it carefully, nodes are connected in different manners, and this connection strategy is different from D1. In fact, as I mentioned, there can be exponential number of such dendrograms that you can compute. Okay, so again recap each of these internal nodes. So all these leaf nodes are the nodes that are present in the graph, but internal nodes indicate, so internal nodes are virtual nodes. These nodes are not present in the graph. Okay, these nodes kind of indicate the association between a pair of nodes or a pair of groups. Okay, so and another thing to note is that every internal node is also associated with a probability PR. Every internal node R is associated with the probability PR. How do you compute PR? We will discuss. Okay, so for R0 there is PR0, with R2 there is PR2, and so on and so forth. Okay, now let us first discuss that how to compute PR. Okay, so PR, let me draw the diagram again, right? At least one of the dendrograms again. Say this is the original graph, A, B, C, D, E, F, and this is one of the dendrograms, A, B, C, E, F. Okay, this is one internal node, this is another internal node, right? So this is R0, this is R1, right? Similarly, say R0 doesn't matter. Say this is R1, right? This is R2, okay. This is R3, and this is R4. Okay. So how do you compute PR0? To compute PR0, we need three quantities. One is ER. Okay, for an internal node R, you need ER, you need LR, and you need RR. Okay, so what is ER? So if you look at this one, right, say this is R. Okay, what is ER? ER is the number of edges in the graph G, in the original graph G, whose endpoints have R as the lowest common ancestor in D. Okay, what does it mean? It means that let's take this internal node, right? It will be easy to explain. Let's take this one. Okay, so this internal node, it has two left children A and B and one right child C, right? We also quantify LR and RR. LR is the left child, RR is the right child, left leaf and right leaf. So for this node R2, LR2 would be 2 number of leaf nodes AB. This is 2. Okay, this is 2. So there are 2 leaf nodes there are two left leaf nodes and there is one right leaf node. Okay. So you have two groups A, B and C. So how many possible combinations are, how many possible combinations you can think of? 2 times 1, AC and BC. Okay, you have two groups A, B and C, right? How many possible combinations can be there? AC and BC. Now out of these AC and BC pairs, okay, how many of such pairs actually are materialized in the form of edges? Means how many such pairs are actually forming edges in the original graph? Okay, so AC and BC, you see that both AC and BC form edges in the original graph, and that is your ER. So ER is the number of edges in the original graph G whose endpoints ABC, whose endpoints have R. So this is R, R2 in this case, R as the lowest common ancestor in D. Okay. So we take an internal node for which we want to measure PR. We look at its left node, left leaves. You also look at its right leaves, and you see how many pairs are possible, right? Now LR is the number of left nodes, RR is the number of right nodes. So LR times RR is the number of is the number of pairs, right? That is possible. And out of LR times RR, out of LR times RR possibilities, right? How many such pairs actually have been materialized in the form of edges? And that's ER. Okay. So that's the idea. So and we will show later theoretically that the optimal probability, that the probability PR would be ER divided by LR times RR, meaning out of all the pairs, how many pairs are there in the graph as edges. Okay. So now let's look at an example. Let us look at this one. Let me erase it. Okay. So let's look at this internal node. So it has LR equals to 1, RR equals to 1. So denominator is 1, and the numerator, so the number of such pairs is AB, right? And AB also exists in this one. So this is also 1. So 1, probability is 1. What about R2? How many pairs are possible? AC and BC. So denominator is 2, 2 times 1, and both AC and BC are there, therefore 2 by 2, it's 1. What about R3? How many pairs are there? So for R3, LR is 3 and RR is 1. Okay, how many pairs are there? AD, BD and CD. So AD is not there, AD pair is not there, no, AD edge is not there, BD edge is also not there, CD edge is there. So the numerator is 1, so this is 1 by 3, 1 by 3 times 1, so 1 by 3. Okay. What about this one? So how many pairs are possible? 4 times 2, 8. And how many of them are actually, exist? AE not there, AF not there, BE not there, BF not there, right? CE is not there, CF is also not there, right? DE is there and DF is also there. So 2, numerator is 2. So 1 by 4. Similarly this one. Okay. Similarly for dendrogram D2, you can compute the same things. For every internal node you can measure the probability. So now we have understood that given a dendrogram, how do we calculate the probabilities of internal nodes? Okay. All right. So if this is understood, then actually you have understood many things. All right. So now let us look at the equations again. So what is the probability that each of these original edges aggregated in ER forming a connections in D? This is PR. PR is something that we calculate, right? PR times e to the power r, PR times ER. What is ER? ER is the number of, actual number of edges. So for every edge that has been materialized, for every pair that has been materialized as an edge, the probability of the connection is PR, right? And how many such cases are there? ER. So the total probability is PR times PR to the power ER. Binomial distribution, right? And how many false cases are there? How many pairs are there which have not been materialized? There are total pairs LR times RR. So LR times RR minus ER, this is the number of pairs which have not been materialized in the form of edges, right? And what's the probability? The probability is 1 minus PR. So 1 minus PR to the power LR RR minus ER. So very same as the, if you remember correctly, this is very same as the ER model that we discussed initially, right, in the network growth model, the Ardov-Srény graph, the random graph model. The random graph model, we derived things in the same way, but there was no concept of PR. There was only one probability, which is PR, which is P, and we said that take a pair of nodes and connect it with the probability P and do not connect with the probability 1 minus P. Now I am saying that the edges, the formation of edges have different probabilities, right? And some edges will be formed with probability PR, some edges will be formed with probability PR dash, and so on and so forth, right? That's the difference. Another similarity is that in case of random graph model, we assume that the graph is formed, I mean each edge, the formation of edges is independent of each other, right? Here also there is no dependency between the formation of edges. It is not the case that the formation of one edge is dependent on the formation of other two edges. It's not the case. Okay. So now, we compute what is the likelihood of a dendrogram. Remember, we can have exponential number of dendrograms. We need to understand which dendrograms are meaningful, right? For that, we need to compute the likelihood. Okay. So the likelihood of a dendrogram D, given the PR, given each such PR values, would be basically product of all the product of this one, product of this quantity for all the internal nodes present in the dendrogram, right? For every PR, for every R we have a PR, for every PR we can compute this one. So that's your likelihood, right? So if this is your likelihood, then what's the target? The target is to maximize the likelihood. So we basically want to get the dendrogram whose likelihood is maximum, right? And we know how to do this. Let us derive this. So we have already seen that the likelihood of a dendrogram is the product over all the internal nodes PR to the power ER 1 minus PR to the power LR RR minus ER. Okay, and we want to maximize this. So we generally take the log likelihood because this bulky product is difficult to compute. We take the log. So log of this L is so it would be sum over all R log of, right, PR to the power ER plus log of, right, 1 minus PR to the power LR RR minus ER. Okay, and then this would be sum over all r. This is power, so this will come outside, log of PR plus LR RR minus ER log of 1 minus PR. Okay, and we want to maximize this, so we want to maximize with respect to PR. So how do we do that? We take the derivative with respect to PR. So say this is F, right? So dF dPR would be what? Would be sum over log, so derivative would be ER times 1 by PR, right? Plus, okay, plus LR RR minus ER times 1 by 1 minus PR, because it's negative, so this would be minus. Okay, so this would be R ER 1 minus PR minus LR RR minus ER times PR by PR into 1 minus PR. Okay. Okay, this would be 0. If it is this 0, then we will see that what would happen. So you have ER minus P. So this PR ER and this PR ER will cancel out, right? So we will have LR RR PR divided by PR times 1 minus PR. Right, this is 0, so it would be PR equals to ER right by LRR. Okay, and this is the optimal value of PR. We have already seen that the optimal value of PR. So we started off by saying that optimal value of PR is this one, right? ER by LRR, but now we derived that why the optimal value is this one. Okay, so if this is the optimal value, then again let's put this PR value here. Let's try to compute the likelihood of a dendrogram D. That would be that would be sum over, let me change my pen, and this is P star, right? So what I will do, I will actually put it here. This is equation 1. So so I will replace PR here by this one. Okay, so in fact what I will do, instead of doing this, better would be to replace ER, right, because ER is LR RR PR star. Okay, I replace ER, okay, by this one. If I do that, in equation 1, this would be LR RR PR star log of PR star plus LR. Why I am deriving this thing? Because a beautiful equation will emerge eventually. You will see this. ER RR minus LR RR minus LR RR PR star log of 1 minus PR star. Okay, this would be R. Okay, LR RR PR star log of PR star plus, if you take LR RR common, it will be this will be 1 minus PR star log of 1 minus PR star. What is this? This is entropy. Okay, of course negative entropy, because entropy is minus P log P minus 1 minus P log of 1 minus P. Okay, so this is R LR RR entropy. So entropy is H. Okay, H PR star, but negative. So this is the likelihood of a dendrogram. Think about it, and we want to maximize this. So we want to maximize this. So this is negative. Therefore, we need to minimize this one. We need to minimize this one. So for which value of PR this will minimize? When entropy is minimized. So entropy curve is this one, right? This is PR and this is 0, this is 1. So entropy is maximum when PR is half, right? So when entropy would be minimum? Entropy would be minimum if PR tends to 0 or PR tends to 1. So if PR star tends to 0 or 1, it would be minimum and you will get maximum likelihood. So what is PR? PR is the probability of an edge, of formation of an edge. So we basically say that higher likelihood dendrogram partitions, I mean if you take the dendrogram which is highly likely, so that dendrogram partitions nodes into groups where connections are either very common, in that case PR tends to 1, or very rare, PR tends to 0. Because if connections are common, then that would be connections within the group, and if connections are rare, then that would be intergroup connections. Okay. Okay. So now we understood that how to compute the PR, right? Now the question remains is how to generate, because since there are exponential number of such dendrograms generated, right? Can we do this thing for all possible dendrograms? No, right? So what you do? So we basically sample out. A set of dendrograms. So there is this process. There is this interesting process called MCMC. This is called Markov chain Monte Carlo process. Using Markov chain Monte Carlo process, what we'll do? We will sample. I'm not discussing what is MCMC. I mean you can just Google it and get a lot of materials. So using MCMC, what you will do? You will sample some dendrograms, right? With probability proportional to the likelihood, right? And let's say you sample 10 such dendrograms with high likelihood. Okay. Now let's assume that you sample these 2 dendrograms, right? Now how do you then use these 2 dendrograms for link prediction? Now let's say you want to understand that what's the probability, you want to predict the link between B and D, right? So what you do? You look at the least common ancestor of B and D in all the dendrograms. B and D, the least common ancestor is this one, and the probability is 1/3. So according to this dendrogram, the probability of formation of this edge is 1/3. According to this one, B and D, 1/9. So the average probability is 1/4 plus 1/9/2. So you take 10 such dendrograms, 10 such probabilities will come, you take the average, and that would be the probability of formation of an edge between the pair of nodes, right? You can do these things for all pairs for which you want to predict links will be formed or not, and then we return top n pairs as your predictions. Okay. So the example, I have already given the example. If you do the same thing, same derivative, you will see that the likelihood of the dendrogram D1 is this one, D2 is this one, and so on and so forth, right. So let us summarize what we have learned. Given a graph, we will create dendrograms. We will use MCMC to sample dendrograms based on the likelihood. How do we get the likelihood? We get the likelihood based on this P's, right. We compute P's based on ER, LR and PR, and then we get the dendrograms. Now given a pair of nodes, we look at the corresponding least common ancestor and the corresponding probability, and then you return. Okay, you take the average and then you return those pairs of nodes which will have higher probabilities. Okay, so that is about this hierarchical right, this some sort of maximum likelihood based method using hierarchical structure of a graph. Okay. Next class we will discuss another algorithm called it is basically the algorithm will use we'll see the algorithm uses the random walk process, and this is called supervised random walk process, right, ASRW, and this is a very famous algorithm for link prediction, kind of a supervised method for link prediction. This is not supervised, this is unsupervised, the one that we discussed today. Okay, with this I stop here. Thank you.